Okay, well, welcome to lecture 13. This is going to be on diode physics. There's not a lot of people here right now, but I guess that's the consequences of lecturing at different times on special days. But anyway, just to start out with some announcements. As usual, homework number 5 is online. That's due next Friday. Lab number 2, the pre-lab was due this week, but due to HSPICE issues, like I was saying before, it's basically before lab section next week. It's due before lab section next week. And next week also, your lab number 1 experimental part is due. And the lab number 2 experimental part is not due till the week of October 5th. I guess in lab number 2, you're only able to do part 1 of that so far. Mainly because for part 2, there was some equipment that we would have wanted to use for that. But since it's unavailable, that was the semiconductor parameter analyzer, we need alternative ways to actually do those measurements. And so we were investigating that with the AD2. And we'll see if the AD2 will even be able to make those measurements. So that's what's happening there. There's some changes being made to part 2. You'll get that soon, I suppose. And hopefully in time for you to actually do that, so that this could be due the week after. So we'll play that one by ear right now. Other than that, any questions about the class, logistics? Okay, so the lecture topics today are diode physics and the operation of diodes. We'll take a look at different regions of operation for diodes, and this is something that we'll see again and again in this class, where we're going to need to pay attention to regions of operation. And so regions of operation means different voltage ranges that we're applying across the device. So in this case, for a diode, the regions of operation we'll look at are zero bias, forward bias, and reverse bias. And then at the end, if we can get to it, we'll talk about diode fabrication to some extent. Last time we finished currents in semiconductors, and the main takeaway from the last lecture was that you have two types of current. You have drift current, where carriers, mobile carriers like electrons and holes, charge carriers, can be driven by an electric field. So that's the type of current that you're used to from previous classes. That's the current that flows through resistors and that sort. But then there's diffusion current. And so diffusion current it's still current. It's still the movement of carriers as a function of time past a certain location. But it's driven by concentration, not by electric fields. And so these two currents we'll have to understand to understand diodes. In particular for diodes, diffusion current is actually going to be more important. So let's go ahead and start diodes then. And so here it is, with a few things written out at first at least. So what is a diode? It's merely a p-n junction. So what does that mean? So we talked last time about acceptor doped materials, which we call p-type, and donor doped materials, which we call n-type. And p-type materials, since they're acceptor doped, they're filled with holes that are free to move around. In n-type material, if it's donor doped, they're filled with electrons that are free to move around. And if we take two pieces of material, one that's doped p-type and one that's doped n-type, and we put them together, that now creates a p-n junction. And effectively, that's what a diode is. It's p-type material and n-type material put together. As you're seeing here, what that means is that there's a huge gradient in types of charge carriers. I have a lot of positive charge carriers on the p side, on the left side, and then a precipitous change from a lot of positive charge to suddenly a lot of negative charge, where these are charged electrons in this case, free to move around. And so what we learned in the last lecture is that anytime you get a situation like this, where you have a huge gradient, a difference in the concentration of one type of thing on this side and the other type of thing on this side, they're just going to want to come together. The holes are going to want to move to the electron side. And so if I wanted to draw this on this plot here, this hole is going to want to go this way really quickly. All these holes will want to go that way quickly. The electrons will want to go this way quickly. And when they get across that, they're going to cancel one another. right? So an electron, we talked about what a hole was and what an electron was. If an electron sees a hole, it's going to combine with that hole, and then you're going to get nothing. It's going to be neutral at that point. And so what happens because of this concentration gradient is you get this current flow. And you can think of this in a couple different ways. We talked about this last time. If I have a huge concentration gradient, this is very far from equilibrium, which means, in a way, we have a very high energy state. Right? All systems want to go to equilibrium, where equilibrium is generally the lowest energy state. And so the system tries to equilibrate to get to that low energy state. Electrons move left, holes move to the right. They cancel each other to some extent. And as they cancel each other, you end up getting what really is responsible for a lot of diode action, which is this p-n junction, or again, that's the p and n type put together, but this is the junction now between the two types of materials. And so I've drawn a little bit more of what happens here. Basically you have a lot of holes on one side, a lot of electrons on the other side, and still in this case, when the electrons see a lot of holes there, they want to move in that direction. So they really would like to go from right to left to join with these holes out here and sort of neutralize those huge gradients with a huge differential in concentration. But you see what happens is that when an electron moves away from this side and goes to that side, it leaves behind a positive charge. Okay, so think of where this electron is. So what we had, and I'll go back to the left side, and let me draw a little something to illustrate this. So what we had was a bunch of atoms. Boy, that's thick. Let's reduce that thickness. And so on this side, each of these atoms has an extra electron, and it let the extra electron go, basically. And so in that case, let me use red to create my electrons here. So I got an electron there. That atom let that electron go. This atom let that electron go, etc. I've got one electron for each atom. Suppose, say I've got a donor material. So I'm really looking at the n-type material on this side here. So that this is corresponding to everything on the right side. So on the n-type side, I have something like this. Well, if these atoms release those electrons, then basically they're positively charged. But that whole n side stays neutral because on average, the electrons, they are moving around. So they're not just staying still. They're mobile carriers. They move around in many different directions here. And their average motion makes this whole thing neutral. However, if because I put these two materials together, I end up with the electrons going to this side, then as the electrons go to this side, they leave behind positive charge. And so after the p-n junction is put together, so let me go to blue again here. When I create that p-n junction, what happens is I'll have these atoms here that are still positively charged, and the electrons have left. The electrons are now somewhere back here on the p side, and they've been combined with holes. So holes came in. Oof. Make that thinner. I guess it's that way because last time I was working on that periodic chart. And they combine with holes, basically. So those go to combine, and they cancel one another out on that side. So at least on the electron side, the n side, what happens is you're left with static positive charge. Okay, and this is the picture that I'm now drawing on this side. So what I'm assuming is I've put this n-type and p-type material together. What happened was all these electrons moved to combine with the holes moved to combine with the electrons. They annihilated each other in these regions here. And so now we're left with positive charge, static charge, and static negative charge here as well. Okay, so when I put the circle around this, I mean that static charge. And so wow. Actually, let's go green. So when I make it circled, that means it's static charge. It's not movable, and that would be the same on this side. If electrons leave this side, they leave behind positive charge. If holes leave this side, they leave behind negative charge. Okay, and so that static charge in this region, and because I've got no charge in this region, we call this the depletion region. Okay, so it's a region of static charge that's devoid of these carriers. All these carriers are still here. Okay, all these carriers are still here. But this area is devoid of carriers. Now, they still want to go through this. This electron sees that hole. It still wants to go across here and join, and the hole vice versa. But what keeps them from doing that now, after enough of this static charge has been created, is, of course, anytime you create that static charge, you're going to create an electric field. So this positive charge and that negative charge, they create an electric field, and so on and so forth. All of these static charges, and there's some positive charge that are joining that, it creates an E field here. And that E field now prevents this electron from moving in that direction and that hole from moving in that direction. So we get to a point of equilibrium because we've got electrons that really badly want to move that way, but they can't because this electric field that's been created by this static charge prevents them from doing it. A carrier, so I'm seeing on the chat, what is the definition of a carrier again? A carrier is a carrier of charge. So maybe I should be saying charge carrier, but a lot of people just say carrier when they talk about this. So it's either an electron or a hole. Okay, electron would be negative charge carrier, a hole would be positive charge carrier. And so let me blow up this picture here just to make that blatantly clear at the bottom here. So I've sort of written what I said here. An E field develops that opposes further movement of mobile charge. And so opposites attract, likes repel. And so if I want to take everything up here and sort of blow it up down here, I might draw something like this. So let me say this is the edge of the depletion region. It's another edge of the depletion region there. And so this may be the central location. This is the point right between the N and P sections here. So this is going to be the P-type material. This will be N-type. Actually, I need to leave myself some room at the bottom here, so let me do this. So this whole side is P-type. And I'm still saying I'm writing it that way because I want to make sure that the depletion region and the mobile charge regions are both represented in the whole type. So P-type and N-type there. Outside here, I've got all these electrons. So these are our free mobile charge carriers on the N-type side, and those are all electrons. On the P-type side, I'm of course going to have a bunch of holes, and these are also mobile, so I'll call them my charge carriers on the P-type side. And then in this region, this depletion region, I've developed a lot of positive and negative static charge. So I guess I could put a bunch of positive charges here. Each of these represents an atom here, and I'm not going to fill this with atoms. I'm just going to say I've got all this positive static charge there. On this side, I've got all this negative static charge, and that static charge is just there because they're coming from atoms. Atoms can't move. Electrons and holes, they are mobile carriers. They can move, whereas atoms cannot. So they just sit there as static charge. And if I've got all this charge here, then of course what I'm going to generate is the electric field. And so up there, right, I'm creating an E field, say from this positive charge to that negative charge. And this starts to get a bit cluttered the way that I've drawn this here. But I essentially have something like this. And so this is my E field that's developed between all of those charges there. Okay, so a couple questions there. Kieran answered one of them. So if they're all positively charged atoms missing electrons, how come the other electrons in the mobile region don't move and fill those holes? I'm going to tell you right now. And so you're right. That question, great question, right? Because this electron right here, this electron definitely wants to move in here. Okay, it would like to move in there, and the reason why it wants to move in there is not just because of, it's because of part of it sees that positive charge there, but the other reason is because it's the concentration gradient. In fact, the concentration gradient is the stronger reason why it wants to move in there. So suppose this electron were able to move in there. So suppose I took an electron, and I guess I'll use a blue color now. Suppose I had an electron right here that managed to get its way in there. Now what's happening? The reason why it got in there is because it had a very strong, and I'm going to erase this positive here so I can create some space for me. It had a very strong force on it that's pushing it in that way, and that force is coming because of diffusion. Just that concentration gradient says that electron wants to move that way very badly. But what's preventing it from doing that is this electric field. The red electric field here that's going positive to negative, that's actually pushing on this the other direction. And so that's drift occurring there, which is current by electric field. So I've got diffusion, I've got drift, that's both tugging on this electron. And when I get just the right amount of positive charge and negative charge here, which means when that depletion region width is just the right width, when I have enough positive charge, I'm going to get just enough field to prevent this electron from heading in that direction. So it wants to diffuse in that direction, but it can't because the strength of the field that pushes it in the right direction, to the right, is equal and opposite to the diffusion potential. Okay, so these two cancel. And when they cancel, I get this equilibrium condition. Where this static positive charge remains, this negative charge remains, and the width of this whole thing is determined by this whole system. It gets to a certain width when all of the electron flow across this stops. I could say the exact same thing about holes. So I could take a hole on this side. I guess I'll draw it up here to get out of the way of everything. It wants to diffuse in that direction, but the electric field, right, holes move in the direction of electric field, forces the hole to drift in that direction, and that all cancels out. So in the end, what I have is this situation where this is all mobile charge. Those are my holes. This is all static charge. It's static negative charge. This is all static positive charge. And this is all mobile negative charge. I'll just call it mobile charge like I did on the other side, but obviously it's negative because those are electrons there. And so we create this system here, and this is sort of zoomed in, but usually we'll draw it like this, where you've got static charge there, you've got mobile charge here, and mobile charge here, and this area we call the depletion region because it's depleted of mobile carriers, and it's a region of static charge, basically, devoid of carriers. Okay, so that's what's happening within our p-n junction. And like I said, a p-n junction is a diode. And so let's review what we're going after. So we now know the physical structure of this. We want to get at this. Remember our diode? So we talked about the diode, a real diode. We talked about the fact that it has this IV characteristic. This is the current. That's the voltage drop across this diode. When my voltage drop across the diode is negative, I essentially have very little current. There's a little bit of current flowing here, and that's sort of modeled by this I sub s. We're going to come up with an expression for that I sub s in terms of physical parameters shortly. it does break down at that point. We won't really talk about this point right here because in the diode we use in this class, we're not really going to worry too much. We will talk about this here, that when our voltage gets positive and positive enough, suddenly we're going to get huge amounts of current flowing through this, and basically it could support whatever current is necessary for the circuit that this is in. And so what we want to do is understand this part here especially. Why is it this part is modeled by this equation? Okay, so by the end of this you will understand this equation to some extent. And so let's move on now and talk about different regions of operation. So this is reverse bias, negative voltage drops across the diode. This is forward bias, positive voltage drops, but mainly positive voltage drops above 0 or mainly above this VD0, which is the turn-on voltage. And then this zero bias point, where you can see at 0, I have 0 current flowing through this thing. Let's first look at the easiest thing, which is the zero bias point. Okay, so from this curve right here, when I put VD across this equal to 0 volts, I get no current. So the IV characteristic is not interesting for this. However, what is interesting is what happens physically within the diode structure. Okay, and so what happens physically is that actually you do get capacitance here. And you get capacitance because remember what a capacitor is. A capacitor is basically charge on two plates that's controlled by a voltage. Well, if I look at this, I've got some charge here, positive charge. I've got some negative charge here. And so I am basically separating charge when I create this thing. And if I were to apply some voltage across this, so right now I've got this shorted, but if I were to apply a little bit of voltage, say I raise the voltage on this side by just a little bit versus that side, what's going to happen is I'm going to get a shift in charge here. I'm going to get a little more positive charge showing up there, a little more negative charge showing up here, and that is exactly what a capacitor does. Okay, but first, before showing exactly how this is a capacitor, let's talk about the physical structure here. So we've already said that what we have is a system where we have mobile carriers and immobile carriers. So in this region right here, I guess I can point here and I can point there. I shouldn't call them immobile carriers because they're not carriers, they don't move. So call them immobile charge there. And in these regions out here, again, I have free carriers. And because someone asked, I'll say free carriers of charge. That's what we mean when we say free carriers. Okay? And so what I want to do is now put a few expressions next to this. So I want to know how much charge do I have here and how much charge do I have here. And so I already gave you a hint that this is like a capacitor. And so if I have the plates of a capacitor, and if I take a capacitor like this and I put a voltage across this, and I get some charge here, so I get plus charge, plus Q there, then on the other plate of this capacitor, I have to have the same charge, minus Q. And that's exactly what's happening here, because the number of electrons on this side that went over here to recombine with holes on that side, they have to be equal. And so already this is looking a lot like a capacitor, but the question is, how much charge do I have here? And for that, I have to understand charge densities. We talked about that yesterday to some extent. If I wanted to write an expression for the total charge that I have here, so all of this charge here, I would write that expression as minus Q, because that's going to be negative charge. That's going to be equal to the unit charge, Q, times the density of charge. I know that the density of charge is just equal to the concentration of acceptor atoms that I have in that p-type material. So that's going to be Q times N sub A, where N sub A we've used before as the concentration of acceptor atoms. And now I want to multiply this, since this is a per unit volume, I want to multiply this by the volume. So the volume is going to be this length, the length of the depletion region here, which I'm showing as X sub P. And we're going to want to get an equation for x sub p, which we're working toward right now. But right now I'm going to use that as a variable. So I'm going to say that's times x sub p. And then this is just a cross-section of my diode. So what I've really done, and maybe I should make that very clear here. That's my PN junction. But let's even go to this point here. I'm sort of drawing this in cross-section. The actual diode that I put together was something more like this. Oops. So I had a p-type material that I put together with an n-type material. So it's three-dimensional like this. P and n right there. And so in this three-dimensional picture, if I want to define my cross-sectional area, I can do it like I've done before. That then is A. And so from there, I'm going to multiply this by A to get volume there. Right? So this is volume, and this is charge density. And that gives me my total charge Q on that side, or minus Q I'm saying there. And I can do the exact same thing for the n-type side. This is going to be positive charge that I'm going to get. And so I can write that the positive charge on, you can think of the positive plate of a capacitor, that's going to be equal to my unit charge times my charge, well, my donor density, which is n sub d, times this distance x sub n, which is not necessarily equal to x sub p. It depends on the charge densities or the densities of dopants on both sides, times that same cross-sectional area A. Okay, well, I'll explicitly, I have it on this thing here. Let's just say that's the area. Okay, and so those are my charges, and again, these charges, they have to be equal. So that charge and this charge I can bring down here, and I can say these must be equal. And with that knowledge, I can continue deriving. And so I can write this charge again, so minus Q, that's going to be Q times N sub A. But now let's express x sub p in terms of the total distance, the total depletion region width here, which I'll call WD naught. Right? So just from the geometry here, you can see that means the total distance. And so what I'm going to use is a parameter kappa, call it kappa p, multiply that by that total distance, where this here represents just the depletion region on the p side. How much of the depletion region went into the p-type material. I want to equate that then to my other charge on the other side, since those have to be equal. And I can write that as Q times N sub D. And I'm going to use another kappa, I'll call it kappa N, times WD naught. This is going to be that distance, that width x sub n of the depletion region on the N side, times my cross-sectional area. I guess I missed my cross-sectional area here, so let me fix this to do that. Okay. And from this, right, I can cancel out the Q's, I can cancel out the W's and the A's, and that then gives me an expression for kappa. So kappa P in particular, is just going to be N sub D over N sub A in this thing. Hold on, my computer's frozen right now, so I'm waiting for this thing. Okay, now times kappa N. Okay, so that's my expression now for kappa P. And that also gives me an expression for kappa N in terms of kappa P. And so what I want to do is get this, basically get some formulations that tell me what the Q is, what the charge is in terms of this WD naught without needing these kappas. Okay, so I want to get rid of the kappas, and so I can just use a little bit of algebra to do this. So first of all, I can write just from the geometry that x of n plus x of p. Again, the definition of WD naught is the sum of those two depletion layers there. We can see that right up here in the figure. With these kappas, I can now write this as kappa n times WD naught plus kappa p times WD naught. That then, from that I can basically say that kappa n plus kappa p has to be equal to 1 in this case. And with this then, I can combine that with this up here. And with a little bit of algebra, I can pull out that kappa n then has to be equal to n sub a over n sub a plus n sub d, and that kappa p has to be equal to n sub d over n sub a plus n sub d. And that means I can write my charge on the n side, which is this, call that Qn, and this is the charge on the p side here. I already have that at the bottom there, so let me... But to write out the charge on the n side here, that now just becomes Q times n sub d. Substitute in for kappa n, n sub a over n sub a plus n sub d, times WD naught times a. So now I have the charge on the n side in terms of the total depletion region width, which is what I was going after. And so I could do the same thing for the p side. I can get the charge on the p side in terms of the total depletion region width. That's going to be Q times n sub a times n sub d over n sub a plus n sub d. Let me make sure that looks like an n sub d. Times that total depletion region width times a. Okay? So this is real physics here, right? We're looking at the physical situation that we have, the physical structure, and we're applying equations now to understand how much charge is developed across this depletion region for a certain width of that depletion region. So if I make this depletion region wider, this charge is going to go up. QP and QN will go up. And so that's sort of the relationship I'm looking for. And now we know that that relationship depends quite heavily on the doping concentrations N sub A and N sub D on the both sides, which we talked about at length last time. And so here I can write a final equation for this. Right, these two have to be equal in the end, and you can see that they are equal. And so I could say these are equal. I can say check. I prove that they're equal here on this. Well, they started out equal, so of course they are. But then I can also write this in a form that might be easier to remember. Because if you look at this just being equal to n sub a times n sub d over na plus nd, well, that really is the same thing as if I wrote it using that parallel operator that we have in circuits. That's n sub a in parallel with n sub d. So if I wanted to really simplify memorizing this equation here, I can just write this as q sub n equals q sub p equals q times n sub a parallel n sub b times the depletion region width times the cross-sectional area of that diode. Okay? Lots of equations, lots of physics being thrown at you kind of all of a sudden. Any questions at this point of what I've been doing here? I'll pause for questions. Okay? I don't hear any, so I'll keep going here. So what I want now, in order to get these charges, I need that WD naught. Okay, so I want an expression for WD naught, and once I get that, I can get an expression for these charges, and that then will allow me to get an expression for an equivalent capacitance, the equivalent capacitance that this is equal to. And so in order to get the expression for WD naught, which is the depletion region width, right, I want that expression. There's a bunch of physics that you need to do that I guess I'm not going to do right now. And I may not do it all in this class because this gets in some deeper physics like Poisson equation and that sort of thing, which some of you may not have had there. And so I'm going to have to ask you to trust some of these physical derivations that are coming out right here. These are things that if you know the physics you can do, but if you don't, then you'll need to trust what I'm saying right here. But basically, because I have these oppositely charged regions here, I have an electric field across these like we talked about. And anytime you get an electric field across these, you get a voltage drop across them. Okay, so what I can now do is relate this width to that electric field and to the voltage drop total across this. And so I'll actually a little later on show you that voltage drop. But for right now, let me just go through the equations here. You get that voltage drop by applying Gauss's law, or by applying the Poisson equation. If you don't know exactly what those are, don't worry about that. It just means you get the voltage drop by integrating the field across this distance here. The field due to these charges across this distance. That will give you a voltage drop. And this is derived in ee130. Okay, in this class we won't go as far as that, but if you want to know how to do that, you do it in ee130. But I'm just going to give you the solution to this. I'm just going to say that the voltage dropped from minus x of p to x of n is often given the symbol phi j, phi sub j. It's called the built-in potential. And they call it built-in because it's really built up by the movement of carriers and the stoppage of that movement because of the fields there. But that built-in potential, which is basically the potential that prevents those carriers from continuing to move, you can think of it that way, is going to be equal to Vt, which is the thermal voltage we talked about. So remember that was equal to 25 millivolts, times the natural log of the concentrations of dopants on the p side and the n side, divided by n sub I squared. And remember, n sub I was that intrinsic dopant concentration. Right? N sub I, from a previous lecture, that's 1.45 times 10 to the 10th per cubic centimeter. Okay, and so you have to square that to get that denominator term there. And that's all obtained, again, from this equation. You're integrating from this point to that point the electric field there. Something that I'm sure some of you can do who've had the physics, but some of you, because it's not really required for this class, don't have that physics, and that's why I'm not going to go and absolutely do that physics now. I'm just going to ask you to trust me that this is what it turns out to be. And you won't need this really for a lot of the stuff we do later on in the class when we're doing circuit design. But right now, it's good to know. What's good to know is that you drop a potential across this because you have an electric field between the plus and minus. And we will return to this concept of potential later on. But right now, that potential then, because it is the potential that stops the electrons and holes from moving, that's that equilibrium potential, it is what determines that depletion region thickness, or depletion region width, right? And so it should not be surprising that for that depletion region width, if I write out the equation for that, which again you need to get by applying the physics up here, but that now ends up being 2 times epsilon s, which is the permittivity of silicon, divided by the unit charge Q, times a function of the dopants in the N and P-type material, and then finally times that potential. Okay? And again, I will say it should make sense that that potential is involved because that's the potential that prevents the electrons and holes from moving. I'll just write that. I'll say it even better than that, from diffusing. across the junction. Okay? Now, I've already alluded to the fact that this is a capacitor. It's a capacitor because it's charged. And this charge is controllable by this potential. Right? And so if I add more voltage in this potential, which I'm going to do a bit later, what's going to happen is I'm going to modulate that charge, which means the amount of charge that I have here can be a function of the voltage across this. But in the end, just the fact that I'm developing two different charges there says it's a capacitor. And I can write this capacitor using this equation in a very familiar way to what you've seen capacitors before. Right? Think of this whole thing that I have on the right as just this. So I have like a dielectric here. That is the silicon depletion region between two conductors around this, where the conductors are right here at the depletion region edges. And I'll have another sort of picture of this later on. But think of this as my depletion region right here. And maybe I'll write that in here. That whole thing is my depletion region in here. The whole thing. That is basically between two plates where you can think you have free carriers here. And so that's like two plates. That's like two metals. You got free holes. You have free electrons here. And so it's like a dielectric between two metals, and that looks like a capacitor. And for that capacitor, I could take whatever its permittivity is, multiply it by the cross-sectional area, divided by the distance between these two, which we now know is the depletion region width. And so that should be familiar to you. This is the formula for a capacitor, where epsilon S is the permittivity of silicon again, that's 11.7, and A is the cross-sectional area of the diode. So what I'm showing you right now is that when I've zero biased my diode, and I'll extend this later on to when I put negative bias across the diode, meaning the voltage across this from the P to the N is a negative voltage, this looks just like a capacitor. And so that looks like a capacitor right now. And so I talked about putting more voltage across this. Let's do that now. Okay, that's what's called reverse bias. So I've left you with, at 0 volt across this, this looks like a capacitor. But as I apply more negative voltage across this, so negative voltage means I'm putting the negative part of the voltage on the P side, the positive part on the N side. So if this were a diode, then actually what the diode would look like, and maybe I should have done this a little earlier, which is you know, where the diode symbol should be. So if I put P and N together here, then my actual diode symbol goes like that. Okay, the P side is this side of the diode, the triangle side of the diode, the N side is the wall side of the diode. Okay, so that's what my diode really looks like here. And so let me go back to where I was there. And now take a look at this same, it's the same thing, except I'm now, instead of shorting this, I'm applying a voltage across this. And this is actually a voltage that's equal to minus V sub D. It's a negative voltage applied to V sub D. So V sub R is equal to minus V sub D. Another way to write this, I suppose, is just to say that V sub D is negative. So V sub D in this case is negative. Okay? And it's equal to minus V sub R. Okay, so if I apply that negative voltage across this, and again, the diode that I really have here is this, from P to N, then I'm going to develop a depletion region, but I'm going to develop a depletion region that's bigger than the previous one. Because instead of just having this phi j across the depletion region, I'm now going to have phi j plus this voltage V sub R that I put across that. So think about this. This is the depletion region with 0 volts across it. That's WD naught that I'm already indicating right here. Right? So that's WD naught, and that's the case with V sub D equal to 0 volts. Now what I'm doing is I'm adding a V sub r to that. So I'm really subtracting V sub r from that V sub d, but I'm putting a reverse bias voltage on this, where the negative is on the P side, the positive on the N side. The reason why I'm being very specific about that is because if I put the positive on the P side and the negative on the N side, something very different will happen. Current will flow. But as long as I've got the negative on this side and the positive on that side, of course, current doesn't flow, just from the diode model we talked about. But what will happen is, because I've got more of a potential drop across this, the diode has to adjust to accommodate that potential drop. And the way that it adjusts is to create more static charge. And the way that it creates more static charge is to push electrodes out of this N-type region, to create a depletion region, and on the P side to push holes out of this region. And when we do that, we create more charge. So you can think of them either as holes and electrons sort of combining more there, or electrons being pushed out of this. And this is the more correct way to think about this. You're pushing the electrons and holes out, and what they do is they go out here and they recombine right there. So they recombine and destroy each other out there. But the end effect is you're creating more of this static charge, negative on this side, positive on that side, which means effectively your depletion region has gotten bigger. So I'm now going to call this WD instead of WD naught, because it's not the zero bias WD. It's basically a depletion region that's gotten bigger. And so if I wanted to think of this in terms of that capacitor that I showed before on this side, so focus on this thing right here on the left side where I'm circling. I'm going to draw little versions of that on the right side. So with my voltage equal to 0 volts, this is that original capacitor. That width is equal to WD naught, and I'm going to have a certain amount of capacitance CJ naught associated with that WD naught. But if I now apply a reverse bias voltage, I now take V sub D equal to a minus VR in this. What's going to happen, I'm showing here, is that this depletion region is going to get bigger. So now, and I'm going to draw this in an exaggerated fashion, now I have a much larger distance between my effective capacitor plates. That's WD, right? So you can see I've got a capacitor like this now, and WD is, of course, larger than WD naught. So what's happened here is I get a new capacitance, CJ, which is less than CJ naught, because I've got more distance between those plates. And so what this is telling you is that I'm changing the voltage across this capacitor, and changing the voltage across this capacitor changes the value of the capacitor, because it changes the distance between those plates. And so I now have a capacitor that depends on voltage, which means it is no longer a linear capacitor, it is a nonlinear capacitor. And so I can write that in terms of equations, which I've done in advance right here. So I've sort of written down what I said. Again, the depletion region width is proportional to the potential dropped across the region. But now the total potential drop, which is this phi j plus that VR, now factors into the same equation. So see this equation here for WD? That's the same equation as the one on the left for WD naught. WD naught only had phi j as that potential drop. But now, because we've added a voltage here, that potential drop is phi j plus V sub r here, okay, which with some algebra and understanding this equation to the left, knowing that that's WD naught, I can factor out the WD naught from here and just write this as WD naught times the square root of 1 plus VR over phi j. And so that's the width. The total width is equal to this. And so the charge, of course, depends on that width through this equation. That's something we just wrote back here. That's this equation up top here. On the left side, I'm circling at the top. And so basically the Q, the charge, is a function of voltage, which is inside this WD. Okay? And it's a nonlinear function. because that WD is a fairly nonlinear function of voltage. It's under that square root. So this is a nonlinear capacitor. And so this is an example of a nonlinear capacitor that we talked about a bit. So we talked about nonlinear capacitance a bit previously, but this is a real nonlinear capacitance, and now you're seeing that semiconductors like this diode, they make nonlinear elements, and this is the first one you're seeing, a nonlinear capacitor. Now, I can continue to write out equations for capacitance, so C sub j then, I can write out as C sub j over square root 1 plus VR over phi j. These are all the same things that I have here, and this is really the same equation that I've got when I plug in WD down here. I'm just writing it out a little more nicely. This now becomes Cj naught, my capacitance, my zero bias capacitance, epsilon A over WD naught. That's the same equation as back here, right? There's that C sub j, and I'm now calling it C sub j naught because I'm doing it at the zero bias voltage. And now you can see it's just modified by this 1 plus VR over phi j, which comes from here, after a little bit of algebra to get here. In other words, you can go from here to here with algebra that I'm not showing you, but I encourage you to do it yourself. So in the end, I can write C sub j as equal to Cj naught, that zero bias capacitance, divided by square root of 1. Now I'm going to substitute minus Vd for V sub r, since V sub r is minus Vd. And so this now becomes the equation for the capacitance across a diode, across the terminals of a diode, which is a function of the voltage that I put across the diode. And if I were to plot this capacitance out as a function of VR, it would look like this. As a function of Vd, it would look like this. And you'll see in this equation, when Vd equals phi j, this is going to go to infinity. That's not physical. So if we had more accurate physics, we actually would see that it does something like this. Okay, but we usually don't care about the capacitance all the way up here. We care less, well, actually that's not true. We will care about that capacitance. But if we're using this strictly as a capacitor, then usually we're in this regime here. When we forward bias this, it'll be in this regime. But we haven't talked about forward bias yet. So a lot of concepts going here, but I think the takeaway for you is that a diode is one manifestation of a nonlinear capacitor. Okay, so with that was a lot. Any questions about this at this point? Okay, so this is your first instance of physics. I think transistor physics, semiconductor physics, diode physics right now. And so if you have more questions, don't be afraid to come to office hours and ask about this. This is the first time you're seeing a lot of these things for a lot of you right now. But hearing no questions, I think I'm going to continue on. Or actually, maybe you're saved by the bell. Yeah, you are. We're kind of out of time. So it's a lot of physics thrown at you right now. I know this because of previous classes or so. So take some time, review this lecture, play it slowly and that sort of thing. You need to digest a lot of this stuff here. And if you can do that this time around, then the next lecture will be a lot easier for you. Because the next lecture, what we're going to do is talk about forward biasing. And in forward biasing, what we're going to do is, instead of putting a negative voltage on the P side and a positive on the N side, you're seeing here, now we're putting the positive on the P side, negative on the N side. We're effectively turning this thing on. And turning this thing on means we're allowing current to flow. And the current is going to flow by diffusion, which is going to be a very different thing for you. Right? Before, all your currents flowed because of electric fields. Now the current is flowing not because of electric fields, but it's flowing because of huge concentration gradients. But that's for next time. I guess we'll end it right here. We're out of time, so everyone have a nice weekend, and I will see you on Monday at our regular time.